Hey class, today we're going to continue on cardiovascular system, and now that we kind of know the anatomy of the heart and how heart pumps through the blood, we're going to learn a little bit more about the physiology of the heart. So how is it able to pump blood, and why does it pump in a specific rhythm? So we're going to learn about the intrinsic conduction system of the heart. For a little bit of background information, know that cardiac muscle contracts spontaneously and independently of nerve impulses. And that's because cardiac muscle actually has special nerve tissue that is kind of like a combination of cardiac and nervous tissue, and you don't find it anywhere else in the body. Even if all nerve connections are severed, the heart is still able to beat spontaneously and independently at least several minutes after you've died and have no brain function. So it's very miraculous feat that this can happen. Now, these are spontaneous contractions, but they do happen in a regular and a continuous way. For example, atrial cells, which are located in your atrium, beat about 60 times per minute, and ventricular cells in your ventricles beat 20 to 40 times per minute. Now, these don't match up on time, so we need a unifying control system to help make sure that these heartbeats are regular. We don't want them to be at two different speeds. So that's where the intrinsic conduction system, also known as the nodal system, comes into play. So two systems regulate heart activity. We just talked about autonomic nervous system in the last chapter, how it regulates automatic responses. These are ones that we don't really have control over. And the autonomic nervous system has your two divisions, parasympathetic and sympathetic, where your sympathetic is going to cause your heart rate to increase if you're in a fight or flight situation, and your parasympathetic is going to cause your heart activity to decrease if you're resting and you're digesting and relaxing. What we haven't really hit on is your intrinsic conduction system or your nodal system. This sets the heart's rhythm. Like I've just mentioned, it's composed of special nervous tissue that is kind of like muscle tissue, but also a combination of nerve tissue, so it's able to be on its own. It doesn't absolutely need the brain in order to pump blood. Now, the intrinsic conduction system also ensures that heart depolarization occurs in only one direction. So that means our signal is only sent in one direction. And that's important, especially since we only want blood to flow in one direction. So what the direction is always going to be atria to ventricles. And when we say depolarization, hopefully remember from the nervous tissue section, depolarization is when an action potential or nerve impulse is sent. So basically all that means is when the heart has a nerve impulse sent, it's only sent in one direction. Now, the intrinsic conduction system is a unifying system, and it enforces the heart to beat as a coordinated unit at about 75 beats per minute. Now, some heart rate might be higher and some might be lower, but on average, a healthy adult is about 75 beats per minute. Now, what does the intrinsic conduction system include? Well, there are several structures within this system. One of the most important ones, and I'm going to start it because it's so important, is your sinoatrial node, which is abbreviated SA. This is located in your right atrium, and it serves as your pacemaker. This is what's going to fire those electrical impulses to cause your heart to beat. It's going to tell you to beat, beat, beat. Now, this is sent throughout your heart through different parts of your intrinsic conduction system. Your sinoatrial node will eventually tie into your atrioventricular node, which is AV. Again, atrioventricular, it's between atria and your ventricles. Once you hit the AV node, the impulse is going to be sent to your AV bundles, known as your bundle of His, where they're going to branch off throughout your interventricular septum, or that septum that separates your two ventricles. And there they're going to fan out to the outside walls of your heart through something called Purkinje fibers to basically send the signal through the rest of your heart muscle. So if you need a little bit of visual, here's one. Here's your sinoatrial node, your pacemaker. It's going to send out a signal. The signal is going to bounce throughout your atrium, and it's going to hit your AV node. From your AV node, the signal is going to go down through your AV bundle, and it's going to split into the bundle branches. So here, this branch is going to go to the right side of the heart. This one's going to go to the left side of the heart. And notice that it happens within the muscle in your septum. And it's going to keep going down where it goes to the outside of your heart. And when we get to the outside of your heart, these are called Purkinje fibers, where they're going to make the outside of your heart contract and push in. So your sinoatrial node, your SA node, starts each heartbeat. We said that it was the pacemaker. And just to put that into perspective, impulses go throughout the atria where it hits the AV node. And this causes your atria to contract. And when your atria contracts, I'm going to add this to your notes, it pushes blood into your ventricles. Once it hits that AV node, your impulse is delayed briefly, so it stopped just very, very split second, and then it continues to travel down through the AV bundles to your bundle branches and eventually out to your Purkinje fibers where your ventricles contract, and this is when blood is ejected or pushed out of the heart. Now, the reason there is this slight delay is because we want to make sure that the ventricles finish filling and those valves close before we push them out to the rest of the heart. Now, your intrinsic conduction system is so important that we have to make sure that it's working properly. So there is a medical procedure called electrocardiography or electrocardiogram, which is ECG. And this is a way to map out the electrical impulses of your heart. So when is your heart firing an impulse to tell it to beat? So a typical ECG has 3 recognizable waves. So over here, this is an example of an ECG. There's the P wave. This happens when the atrial depolarizes, or basically the atrium contract. The QRNS complex is called QRNS. It starts low and goes high and then goes down here to the S. This is depolarization of your ventricles. So this is when your ventricles contract. So notice that when your ventricles contract, it's a lot higher. And then the T wave is when the ventricles are repolarizing or they're resetting themselves. So abnormalities in the shape of these waves or the timing, so how long it takes these waves to occur, can tell you that something is wrong, or it can also be an indication of a myocardial infarct. I'm not going to say that right. And basically, it's a heart attack. Now, there are a couple things with your intrinsic conduction system. If you have a rapid heart rate, it's causing your heart to send impulses to cause it to beat fast or over 100 beats per minute. This is known as tachycardia. Prolonged tachycardia may actually progress into fibrillation, which is basically a rapid, uncoordinated quivering of the ventricles, and they're trying to pump blood, but the heart can't. And then you have bradycardia, which is the slowing of your heart rate where it's less than 60 beats per minute. You're not getting enough heartbeats to pump blood to the rest of the body. And then after the intrinsic conduction system, the other thing that we're going to hit on before we finish this lesson is the cardiac cycle. Now, a cardiac cycle refers to one complete heartbeat. And when we have one complete heartbeat, that means both atria and ventricles have contracted and then relaxed. So there are words we use to refer to when something contracts and when something relaxes. Systole is used to mean contraction, so something is contracted. Diastole is when your heart is relaxed. Now, we already mentioned that our average heart rate is about 70 beats per minute. And another important thing to notice here is your cardiac cycle is 0.8 seconds. So for one complete cardiac cycle where blood leaves the ventricles and comes back and contracts, takes 0.8 seconds. Okay. So cardiac cycle includes 5 major events, and we're going to go through each of these events separately. The first is atrial diastole. So again, diastole is relaxed. So this is when your atrium are relaxed and blood flows into your atrium passively and goes down into your ventricles. So heart is relaxed, pressure is low, blood flows into the atrium down into the ventricles, and they're able to do this because your atrial ventricular valves are open. Your semilunar valves, on the other hand, are closed because we want the ventricles to keep filling in for it not to go out the other side. Think about if you're filling a bathtub, you have to plug the hole to the other side. The next thing we have is atrial systole. So systole, this again means contract. So while your ventricles are still relaxed, this is where your atrium contracts and blood is forced down into the ventricles to finish the filling process. It's kind of like toothpaste. You have to squeeze the little bit of toothpaste out of it to finish getting it out of that tube and onto your toothbrush. The third step is isovolumetric contraction. So iso usually means that it's balanced. Contraction is where things are going to is used because we have isovolumetric relaxation. So this is right before the ventricles are going to contract. So atriosystole ends, so it's no longer contracting. However, ventricle systole or contraction has now begun. This is where your ventricle is going to start pumping out blood to the rest of your body. Well, during this phase, this is when pressure rises, our AV valves start to close. And then this is where both valves are closed, both semilunar and AV valves. So right there, that's when blood is completely only in the ventricles before it's about ready to be pumped out. And when it actually gets pumped out is called ventricular systole. So remember, systole, you're contracting. This is also known as your ejection phase. So this is where your ventricles have contracted and it's pumping blood out of those major arteries, leaving the heart. The semilunar valves have to open in order for blood to actually leave that part of the heart, and blood is ejected. And after it is pumped, at the end, we have to start that process over again, so atria begin to relax and fill with blood. Okay. And then we have isovolumetric relaxation, where your ventricles then, after they've contracted, relax as well with the atria, and pressure falls below. Semilunar valves close, and for another moment, all those ventricles are going to, all those valves are closed, so atria is filling. And then when atrium get enough water pressure in it, then your AV valves open and that blood starts going down into your ventricles just to start the process over again. So here, this picture is so much better representation than just following words. Here, atrial diastole, this is when blood in your atrium fill the blood in your ventricle. Atrial systole, this is when here, this shows that the arrows show that it's contracting. And here it's pushing blood from your atria down to fill your ventricle. Then you get over here with isovolumetric contraction. Notice that both your blood vessels are, your blood valves are closed. And then when you actually, you have ventricular systole, this is where it's actually ejected. So it's pushed out. And notice that your atria is starting to fill again. And isovolumetric relaxation, your atria are finishing filling, where they'll eventually start over and open up, and they'll go down to your ventricles. And that brings up heart sounds. When you use the stethoscope, you can hear 2 distinct cardiac sounds: lub-dub, lub-dub, lub-dub. Lub is your first sound. It's usually louder, it's longer, and that's caused whenever your AV valves close. And dub is a short, sharp sound that you can hear whenever the semilunar valves are closing at the end of ventricular systole, or after your ventricles have actually pumped blood to your body. So pretty sounds they like to listen to see if there's any issues with your heart. Lub dub, lub dub. Okay, so that's the end of today's lesson. Let me know if you have any questions, and I hope you guys have a good day.